A bridge can look rigid from the road while its main girder is already bending. That is not a contradiction. The important question is not, does it move? Every loaded structure moves. The question is, what kind of movement is this, and what changes before the structure finally loses its load path? Start with one truck near the middle of a simple span. Its tire force enters the deck, spreads into the girder, travels to the bearings, then becomes reactions at the piers and ground. The girder is not just holding a weight. The offset between that load and each support creates a turning effect, a bending moment. For this idealized span, the positive bending moment grows toward midspan and peaks under the truck. Near the supports, the reactions are large, but the midspan bending moment is smaller. That is why the center of a simple girder is the first place to look when explaining a downward sag, while the support region has its own shear and connection problems. Take a slice through the girder. As it curves downward, the top fibers follow a shorter path and go into compression. The bottom fibers follow a longer path and go into tension. Between them is the neutral axis, the line where the longitudinal bending strain is approximately zero. The whole section does not move equally. It rotates around that internal balance. In the elastic beam model, bending stress is sigma equals my over I. M is the moment, y is distance from the neutral axis, and I is the second moment of area. So the stress is nearly zero at the neutral axis and largest at the outer surfaces. Add load, and this stress gradient grows before anything has broken. Here is the less obvious part. I is not just how much material you bought. It is how far that material sits from the bending axis. Put steel into top and bottom flanges and use a thinner web to keep them apart, and the same material resists curvature much better than a flat strip. That is why bridge girders look tall. Depth buys flexural stiffness. For a simply supported beam with a center point load, the idealized midspan deflection is PL cubed over 40 ADI. The cubic is the surprise. Using 100 kilonewtons, 200 gigapascals of steel, and a section with I of 0.18 cubic meters, a 30-meter span gives about 1.56 millimeters in this toy model. Double only the span, and the result becomes 12.5 millimeters, 8 times larger. These are illustrative beam numbers, not a bridge rating. Engineers therefore ask two different questions. Can the member resist the required stress without reaching a strength limit? And does it stay serviceable? Does it deflect, crack, vibrate, or deform enough to harm rideability or durability? FHWA design examples check live load deflection and cracking at service limits even when those deformations are not, by themselves, collapse. In a concrete or composite girder, rising tension can open flexural cracks near the high moment region. The concrete on the cracked tension side no longer acts like the original uncracked block. Reinforcement carries the tension, and the effective section and neutral axis calculation change. The same load can now produce more curvature. The crack is a state change to interpret, not an instant collapse stamp, and not something to ignore. The most useful warning is often a change in the load deflection response. An elastic girder follows a roughly straight line and returns when the load leaves. After cracking, yielding, corrosion-related section loss, local buckling, or a damaged connection, the slope can fall, and some deformation can remain. A redundant bridge may redistribute load after one member is damaged. A non-redundant path may not. That is why it is still standing is not a complete diagnosis. So read a bridge bend in order. Where is the bending moment? Which face is in tension? How much stiffness does the section have? Does the movement reverse? Or has the response changed? And what load path remains if a member or connection is damaged? The bridge bends before it breaks because deformation is the first visible consequence of force and geometry. Failure comes when the material state, stiffness, or load path can no longer support the next increment of demand.